Seesaw, Marjorie Daw. What has that to do with cantilever bridges? A whole lot. A seesaw is a cantilever beam. Place a weight on one end, and the other end can support an equal load. Add another seesaw and replace the inside weights with a short beam which spans the gap, and we have a bridge, a miniature cantilever bridge. And if we were Lilliputians, we could ride across. That is, if we invited traffic by tying the weights to the underside of the beams. Simple, isn't it? Now let's get technical. Engineers call these fulcrums or pivotal points main piers. The weights or anchorages at the ends, the anchor piers, to which the ends of the bridge are generally anchored. The parts of the beams between the anchor piers and the main piers are the anchor arms, and reaching out like extended arms trying to tag each other are the cantilever arms. The gap is filled with what engineers call the suspended span, supported by the cantilever arms. This is a typical cantilever bridge. Our land is laced with thousands of cantilever bridges spanning rivers and other obstacles. These bridges are found in many forms: beam and girder cantilevers, and truss cantilevers. Most cantilever structures are built up of through trusses or variations of through trusses. A through truss is so designed that the traffic passes through the structure rather than on top of it. Many bridge designers prefer this type of structure where moderate main spans of 800 to 1,200 feet are necessary. One of the principal reasons for this preference is simplicity of design and construction. Because of great rigidity and economy, the cantilever bridge has often been chosen for railway spans over wide navigation channels. It is able to withstand minor foundation movements without changing the stresses set up in its truss members, and it can be erected without interrupting navigation. Cantilever bridges are not a new development. They've been used for hundreds of years. The most famous of all cantilever bridges, the Firth of Forth, was built by Scotsmen back in 1890, which certainly speaks well for the economy of this type of bridge. Its tremendous 1,700-foot center span set a record that it held for 27 years. In 1917, this record was finally broken when the Quebec Bridge, with a center span of 1,800 feet, was thrown across the Great St. Lawrence River. The East Bay crossing of the San Francisco-Oakland Bay Bridge, built by American Bridge, features the longest cantilever span in the United States. It's a double-decker with a center span of 1,400 feet. Its upper deck carries passenger cars, while the lower deck handles trucks and interurban electric trains. It carries one of the heaviest traffic loads in the country. In 1954, plans were ready for the construction of our country's heaviest cantilever bridge, spanning the Hudson River at the Tappan Zee to join South Nyack and Tarrytown with a gracefully curving bridge 3 miles long, including its approaches. This bridge was to link the east and west sections of the great New York State Thruway, connecting New York City and Buffalo. To build a bridge the size of the Tappan Zee in less than a year required adroit engineering and demanded a mastery of logistics calling for perfect timing and synchronized flow of materials, fabrication, and delivery at the site of construction at just the right time. Not too soon, not too late. To meet this tight schedule, 5 American bridge plants sprang into action simultaneously. From Ambridge, from Elmira, from Trenton, from Gary, and from Roanoke came a steady procession of railroad flat cars converging on time at the depot selected for material sorting and storage, Weehawken and Hoboken. Next began what was perhaps the greatest bridge floating operation ever attempted. A flotilla of barges moved the fabricated members for 164 beam approach spans and 19 completely assembled deck truss spans to the bridge site. The deck truss spans weigh almost 1,000 tons each, are 91 feet wide, 28 feet deep, and vary in length from 232 to 247 feet. So big that 2 huge railroad car floats were required to carry them. Mother Nature donned a bridgeman's hat and helped out at this point. High tide permitted the spans to be floated into place precisely over their final designated positions. Then, as the tide receded, the car floats lowered the spans onto their piers. When necessary, final adjustments were made by pumping water in or out of the car floats and by operating 500-ton jacks provided for that purpose. As soon as the steel for the approaches was permanently placed and riveted, the concrete started to flow in preparation for the final surfacing of the roadway. While the erection of the thousands of feet of approaches was in itself a great achievement, the star role in this dramatic performance goes to the great balancing act, the construction of the cantilever portion of this giant bridge. At the locations chosen for the foundations for the 2 main towers and the 2 anchor towers, solid rock was so far below the riverbed that conventional foundations were impractical. Instead, the main piers and anchor piers under the Cantilever Bridge were supported on cellular reinforced concrete boxes, resting on the river bottom with their tops approximately 2 feet below low water. These concrete boxes are called buoyant caissons. From these, steel pipes filled with concrete, some as long as 295 feet, extend down to bedrock. The largest of these buoyant caissons is 100 feet wide, about 200 feet long, and weighs about 16,000 tons. 80% of the dead load of the main bridge is supported by the buoyancy of the caissons. Generally, the first operation in the construction of a cantilever bridge is the placing of the falsework or temporary supports for the anchor arms. Falsework usually consists of a series of piles driven down to bedrock to support the anchor arms. However, conditions may dictate that a fabricated falsework span be placed between the anchor pier and the main pier to support the anchor arm during construction. Where practical, actual bridge approach spans are used as temporary falsework. This was done by American Bridge in erecting the cantilever portion of the Sunshine Skyway, which spans Tampa Bay in Florida. This dual use of material, incidentally, is but one of many cost-saving devices available to alert bridge engineers. Here we see the falsework in its temporary position under the anchor arm. After the 2 anchor arms were erected, the falsework spans had done their job and were floated to their permanent positions in the bridge as approach spans. There, the spans were eased into place by jacks, and water pumped in or out of the barges either lowered or raised the spans onto their piers. And here they are in their final locations. But the Tappan Zee approach spans were not suitable to serve as falsework, so the engineers designed 2 expendable temporary falsework spans which were assembled at Grassy Point. Each span is 93 feet wide and over 500 feet long. Each of these enormous falsework structures weighs 1,500 tons. The falsework was floated into place and supported on the edges of the concrete caissons of the main foundation structures directly underneath the anchor arm locations. The steel towers which will support the bridge were erected by crawler cranes mounted on barges and derrick travelers operating from the falsework. With the main towers completed and ready to serve as fulcrum points, the balanced erection or seesaw method of construction begins as soon as the first section of the superstructure is placed. A precise record is maintained, a sort of daily ledger of the material erected, its weight, the location of the center of gravity. And a check is kept of the changing stresses in the falsework at all times by measuring the deflections at the center of the falsework spans. The building of the superstructure moves out simultaneously from each of the main towers, with the derricks working in opposite directions. Weight balance is precisely controlled to avoid overloading the falsework. The anchor arm just enough heavier than the cantilever arm to prevent the bridge from teetering during construction. A miscalculation here would cause quite a splash. It's tough enough to build a bridge by the delicate balanced erection method, but throw in a couple of devastating nearby hurricanes, namely Connie and Diane, ladies in name only, at a time when the structure was at its most critical erection stage, and you can see that there must have been some king-size headaches for a while. In this type of construction, the further apart the derrick travelers, the greater the progress. They move in opposite directions until the entire anchor arm and a portion of the main span are erected. Those derrick travelers weigh 350 tons apiece, including the big stiff-leg derrick and the guy derrick, which rides piggyback to do the lighter work behind the big fellow. As the bridge progresses, the role played by the temporary falsework becomes more apparent. Notice how the jacks mounted on the falsework hold up the load above. They were designed to support, in addition to their own weight, about 1,000 tons of unbalanced load during construction. This bridge is so massive that it dwarfs the men putting it together. Look close and you can see them, way, way up there. Those aren't just men, they're bridgemen, a fearless breed. Sure-footed as cats, with the brawn and skill necessary to build the bridges which contribute so much to our progress. Here comes a boatload to take over the late shift, replacing the early morning crew. The erection of the Tappan Zee Bridge required 300 of these bridge building specialists working 2 8-hour shifts during the long summer days. Just climbing to their stations requires more physical effort than most of us put out in a day. Then they really start to work. It's a safe bet that not many bridgemen are overweight. Here's the bridgeman's elevator. Going up. He's not worried, nor should he be. He's safer up there than most of us are going upstairs in our own homes. One of the advantages of spanning a river with a cantilever bridge is that river traffic is not interrupted. The nature of the construction is such that the channel is always open to shipping and fishing. There goes a secondary bracing member moving into position. That hand signal says, "Keep it coming, you're doing okay." Because of construction noises, winds, and distances too far to be heard even when shouting, these bridgemen depend on hand signals. With huge steel members swinging through the air, these signals must be right and right on time. Another example of the teamwork required in this rugged business of building bridges. Every steel member designed for the bridge has an identifying mark and is waiting on a barge below when the call for red iron comes from above. Then 150-ton capacity derricks hoist the member at the same angle at which it is to be fitted into its truss. Engineers have computed the point at which a hitch is to be fixed for lifting. This positions the member in such a way that a minimum of time and effort is required to guide it into place. Every step has been carefully planned by American bridge engineers, and every member is erected in the exact sequence specified. During construction, the members are often subjected to greater loads than they will have to bear even after the bridge is in use. As each member is lifted into place, bridgemen known as connectors lose no time in ramming home bolts or drift pins to temporarily hold the member in place until the bolts or drift pins are replaced with white-hot rivets. And here's the answer to a call for more rivets. Rivets the exact length and diameter specified and made from the right steel for the job. This bridgeman, known as a heater, is really a rivet chef who too does the rivets to a turn. He can tell by the color when the right temperature is reached. The rivets in this forge are heated to a temperature of 1900 to 2000 degrees. If it's too hot, the rivet will burn. If it's too cold, it will not drive properly. Tossing hot rivets is no job for an amateur. This is big league stuff. Every pitch better be a strike right over the plate and no umpire to call it. If you think the last pitcher was hot, just watch this fella toss a few over. Up and over, right into the steel mitt. There's another way of delivering hot rivets when it's too long a pitch for the heater, when the catcher may be out of sight, maybe up on the top chord of the Tappan Zee Bridge, about 155 feet above the pitcher down on the bridge floor. It's really simple. Just drop a hot one into a pneumatic tube. It works just like in a department store. And with the aid of the tube, he curves him right to the waiting riveter. Most shop rivets are driven by huge pneumatic or hydraulic riveters, but they're far too large and cumbersome for use in the cramped areas that bridgemen move around in, so they use smaller, easier to handle riveting guns. The riveter's teammate, the bucker-up, crawls through one of the manholes into the member and pushes hard against the head end of the rivet while the riveter shapes another head on the other side. Since the rivets are just the right size, there's just enough metal to form the other rivet head. Too little or too much would be unacceptable. Here are just a few on this bottom chord. It takes a lot of field rivets to assemble a bridge, almost 300,000 on this cantilever alone. And that doesn't include the hundreds of thousands driven in the shops. As the anchor arms reach closer and closer to the anchor pier, the importance of the falsework becomes more obvious. These temporary support points with their built-in jacks make it possible to extend the arms right out to meet the anchor towers. Tie-downs, capable of resisting an uplift of 750 tons each, are attached to the ends of the anchor arms, and the jacks are freed of their loads before erection proceeds beyond this point. The falsework truss has now served its purpose and may be removed at any convenient time. And there it goes. This high-level conference session to determine the next member to be installed. These bridgemen aren't worried. They know from past experience that every piece will fit into the jigsaw puzzle if the right member is put in the right place at the right time. And behind the lines, engineers on the drawing boards and in the designing and erecting offices have left nothing to chance. They even know the exact batch of molten steel from which every member was made. And they know that each member was made and rolled to their exacting specifications. It's all on the record. The template makers, too. The men in the shops. Each is proud of his part in building the great Tappan Zee Bridge. It won't be long now. Here's the next to the last bottom chord about to be raised. There goes more than 100 tons of steel in perfect balance. These giant steel links or connecting plates fastened at one end play an important part in the final closing of the bridge. An exciting moment for all bridgemen is the preparation of the bottom chord which will tie the two cantilevers together for the first time. The American flag proudly announces to the world that this is the member which bears the honor of closing the span. There's still plenty to be done. but the Hudson has been bridged. Every man will remember for the rest of his life that he helped bridge the Tappan Zee. We don't know the name of the first man across, but you can be sure his grandchildren will know about it. When the center span is closed, the bridge is not yet complete, for the engineers have intentionally left a small space at the center of the bridge to compensate for rolling and fabrication tolerances, temperature changes, and other factors. To close the gap and complete the job, there remains one very intricate maneuver. Engineers call this swinging the suspended span, and that's just where those connecting links prove their importance. By adjusting some built-in jacks, the two halves of the suspended span are rotated slightly. The elongated holes in the bottom cords allow enough room so that the center of the bridge can be lowered into its final position to become a simple truss span hanging from the ends of the cantilever arms. In many cantilever bridges, the center suspended span is well defined and can be easily recognized. But in the Tappan Zee Bridge, the suspended span blends so smoothly into the cantilever arms that it is difficult to distinguish. Over 30,000 tons of steel went into the erection of this great cantilever bridge. That's more than twice the amount of steel required for the 39-story United Nations Secretariat building in New York City. Today, spanning the broad Tappan Zee is this beautiful structure, one of the 75 bridges built by American Bridge on the New York State Thruway between Rochester and the Hudson. This elevated road with its gently flowing curves provides safe travel for millions of motorists over a great modern highway linking New York City and Buffalo. It was created not only for today's heavy traffic, but with an eye to the future. Its 6 lanes will care for tomorrow's traffic as well. Its graceful S-curve can be interpreted as a symbol of the safety uppermost in the minds of the bridge builders. Witness the 2 broad 37-foot roadways, each accommodating 3 wide traffic lanes. The 10-foot center mall, which separates opposing traffic and also provides room for disabled cars. And the 3-foot safety walks on each side, just in case of emergency. This handsome cantilever bridge is as safe for motorists as modern engineering science can build. And it is made of steel, the only construction material that could translate such ambitious plans into this magnificent reality. Seesaw, Marjorie Daw. The Hudson has a new master.